Hello and welcome back. So this was the code which we developed in the previous session, and we solved a very simple problem, a Laplace kind of problem in FEniCS by using this code. So let me just run this code once again. So this was a very simple sort of problem, a Laplace kind of problem. So we are interested in only del square phi is equal to 0, where phi is your unknown, and you are just prescribing some Dirichlet values of phi on these boundaries. And this is in an infinite domain. So we just truncate the domain at a radius which is sufficiently far off from the origin. So this circle is the larger one is placed at the origin. So this problem is pretty well behaved once we use a circle which is almost 10 times this radius. And we know there is an analytical solution for that. So we compared our flux values. So this is what we did in the previous session, and now I just want to use this problem for some very simple eigenvalue analysis. And so this will be done by using the SLEP-C eigensolver. So this is a solver which comes packaged along with PET-C. So PET-C is this very robust parallel computing library which comes along with FEniCS. It's really powerful, and SLEP-C comes packaged alongside, so we can use it for some very simple basic eigenvalue analysis. And these will just be a carousel of codes. So we developed this first one from scratch, where I just explained it line by line. So here I'll not do that because I think we are already familiar with most of the syntax. So I'll just explain where I'm adding these snippets which are piggybacking on top of this previous code, and we'll just explain them and we'll just show the results. So first we'll just do a very simple eigenvalue analysis, and then we'll identify the modes which are the most important, and we'll just truncate the model and build a reduced order model from those modes. So very simple process, and of course in industry you are going to use a much more complex process for your reduced order models. So you will be using snapshot based analysis, because in industry you won't get these kind of problems which are Laplace kind of problems. So most of the problems will have some non-linearities. So the Laplace problems might be the starting point to analyze any system, but you will of course go into more complex behaviors, and so that's why your matrix in your Laplace problem, you will get a very nice symmetric positive definite kind of matrix, and so your eigenvalues will also be very well behaved. So you have no complex values coming in, but the moment you make the problem non-linear, it has convection inside it, and so it will really become quite complex, and you can't just use a simple eigenvalue analysis for building a reduced order model. So in principle probably you could still maintain the symmetric positive definite kind of structure by using something like the least squares kind of finite elements, but I don't think these kind of solvers are really used that often, and it's I think quite a niche application, and of course it has its own drawbacks, like mass conservation is not really good in that case. So in this case we'll just be using this like a pedagogical tool. So this is just for motivating the idea behind ROMs, because ROMs are a hot topic, and this will just give us some nice motivation towards that. So let's just begin this step by step.